Welcome everyone to this week's video on the robotic exploration of the moon. My intention with this video is to provide you a good overview of the history of the robotic exploration of our moon. The overall objectives, the learning objectives I'd say, are to be familiar with the moon missions that have explored the moon in the 21st century and their milestones, to appreciate the continuity and relationship between the major missions or how they've built off of one another, and finally to understand the major findings related to the physical geography of the moon over the past 25 years, namely the discovery of potential water ice. So based on previous videos, by now you should already be familiar with the moon's formation and its general geological history. And in past videos on the space race, I talked a lot about the earliest missions from both the American and Soviet programs in the 1960s and 70s. And of course, we've also already talked about the Apollo program, the first and so far only human missions to visit the lunar surface. In this video, we're going to jump ahead a little bit all the way to the 20th century and the mid-2000s. So this means we're skipping right over the 1980s and 1990s. But in all honesty, there was very little going on at the moon in those decades, with the exception of the U.S. Clementine mission in the 1990s. In fact, not a single mission was launched to the moon by any country during the entire decade of the 1980s. So we're about to jump in to what is really the early days of the golden age of lunar exploration, in that since 2007 there's been a constant robotic presence in orbit around the moon, and more recently a constant robotic presence on the surface of the moon, as we'll see. So let's get started now by going all the way back to 2007, as I mentioned, and looking at a sort of preview video for what could be argued to be the first major 21st century lunar exploration mission. I want to show this entire video. It's a little bit long because it also provides some helpful explanations for what many of the instruments on board spacecraft like Kaigua, which you're about to become familiar with, and all the other spacecraft we talk about today. This video helps explain a little bit about what they do. Now for this class, we don't need to understand exactly what each instrument on every spacecraft does. In short, spectrometers tell us what things are made out of chemically. Altimeters tell us how far something is from a spacecraft, which allows us to do terrain mapping and 3D models. Magnometers, gravitometers, and particle detectors should be self-evident. And of course, cameras typically provide images akin to what a sighted person would see if they were where the spacecraft is. So anyways, let's learn about Kaigua and all the other major missions that have explored the moon in the 21st century.
The launch of the first artificial satellite in 1957 catapulted mankind into the space age. One after another, unmanned probing and manned space flights were carried out to explore our cosmic frontier, culminating in the legendary explorations of the Apollo program. In the Apollo program, highlighted by the first successful human landing on the moon, many on-site science experiments and returned samples brought us a lot of new discoveries and views of the moon and terrestrial planets. We learned, for example, that the moon emerged about the same time as the Earth, some 4.5 billion years ago, and that the surface geology of the moon greatly differs between its near and far sides. The Apollo program came at the height of the Cold War, a geopolitical and ideological struggle between the United States and former Soviet Union that politicized space exploration, turning it into a race to the moon. Eventually, with the end of the Apollo program, many of the questions and mysteries about the moon have gone unanswered. The Selene-Kaguya program began in 1999 with the intention of re-examining the questions long left over by the Apollo program. Questions such as, how was the moon born, and how did the moon evolve into what it is today? When the Selene is launched in 2007, it is hoped we can get closer to the core of the mystery of the origin and evolution of the moon. Selene is a lunar explorer mission to be organized primarily by the Japan Aerospace Exploration Agency, JAXA. It will be the most sophisticated and thorough lunar exploration mission undertaken since the Apollo program. The primary objectives of the mission will be to conduct a global observation of the Moon to provide scientific data to investigate its origin and evolution. The Selene will perform precise observations and analyses of the distribution of elements and minerals on the Moon's surface, its surface and subsurface structure, its gravity field and remnant magnetic field, as well as its surrounding plasma, energy particles, and lunar ionosphere. In addition to scientific objectives, the data accumulated by Selene should serve as a basis for mankind's future utilization of the Moon. Selene will also look to establish fundamental technologies for future Moon exploration missions, such as lunar polar orbit insertion, three-axis attitudinal control to enable variable lunar orbital rendezvous, and various thermal controls needed to withstand the extreme variations in temperatures between lunar day and night. So what exactly will the mission of the Selene consist of and entail? Selene will consist of a main orbiter and 2 small satellites. At launch, the rectangular-shaped main orbiter will weigh approximately 3 tons and will be approximately 5 meters in height and nearly 2 meters in length and width. Its solar panel will be capable of generating approximately 3.5 kilowatts of power. The main orbiter will be sent to a circular polar orbit at an altitude of 100 kilometers. The 2 small satellites will be octagonal cylinders measuring 50 kilograms in weight, 65 centimeters in height, and 1 meter in diameter. The relay satellite will be sent into an elliptical orbit around the Moon with the Perilune and Apolloon altitudes of 100 and 2,400 kilometers respectively. The other VRAD satellite will also circle the Moon, but with the altitudes of 100 and 800 kilometers respectively. The main orbiter with the 2 smaller satellites will be launched together by an H-2A rocket. Once launched into space, the solar paddle and high-gain antenna of the main orbiter will be deployed, and the Explorer will orbit the Earth twice before being inserted into a transfer orbit toward the Moon. At this point, initialization checks for onboard mission instruments will take place. Once within proximity of the Moon, the main orbiter will decelerate and settle into a circular lunar orbit. The 2 small satellites, the relay satellite and the VRAD satellite, will then be released into 2 identical elliptical orbits. Once the main orbiter is circling the Moon at an altitude of 100 kilometers, it will sequentially deploy LRS antennae and lunar magnetometer mast, marking the start of a series of scientific observation missions. Selene will study the Moon in its entire surface for about 1 year. The Selene will conduct 15 observation missions. These include a global observation of elemental and mineral distribution, topography and subsurface structure, gravity and magnetic fields distribution, as well as lunar surrounding environments through highly sophisticated, high-resolution technologies. To study elemental distribution on the lunar surface, X-ray spectrometer, XRS, and gamma-ray spectrometer, GRS, will be deployed. The X-ray spectrometer will observe the energy of X-rays characteristic of elements excited by irradiation of solar X-rays to the Moon's surface, and conduct a detailed investigation of the major elemental distribution in moon rock, such as magnesium, aluminum, silicon, and iron. The gamma-ray spectrometer will create a comprehensive distribution map of lunar elements using a high-performance germanium detector to observe gamma rays. It will determine rock type from major elements such as silicon, iron, titanium, and oxygen. The presence of hydrogen can also help to determine whether or not large amounts of ice exist in the polar regions of the moon. Because radioactive elements such as potassium, thorium, and uranium are concentrated in liquid leftover from the period of cooling and solidification of the moon's magma, the GRS can gain clues into the thermal evolution of the moon. Two mission instruments will be used to examine mineral distribution on the moon: multi-band imager, MI, and spectral profiler, SP. The multi-band imager will take multicolor images of the moon's surface through a 9-wavelength filter covering visible to near-infrared light. From the color difference, the mineral composition of the lunar surface and their distribution can be clarified. The spectral profiler measures the continuous spectroscopy of visible to near-infrared light to obtain the variety and abundance of minerals on the moon's surface. The combination of these results with those of the multi-band imager will enable a precise mapping of lunar mineral composition and distribution. Three instruments will be deployed to study the moon's surface and subsurface structure. They are Terrain Camera, TC, Lunar Radar Sounder, LRS, and Laser Altimeter, LALT. Photographs of the lunar surface will be taken from the Terrain Camera, a pair of cameras on the main orbiter pointed at oblique fore and aft angles. The cameras have a spatial resolution of 10 meters. The disparity between the two images taken of identical locations will enable the digital terrain model of the entire moon surface. For the Lunar Radar Sounder, 4 15-meter-long antennae are extended from the main orbiter in orbit around the moon. For so-called sounder observation, 2 antennae will send 5 megahertz pulses, which will be bounced off the moon. Analysis of the returning radio signal should provide a picture of the moon's subterranean structure up to a depth of 5 kilometers. For natural radio wave observation, 4 antennae will be set to receive various signals. Low levels of noise at the far side of the moon makes observation of natural radio waves from the sun or other planets a highly effective form of measurement. The laser altimeter will send out laser beams toward the lunar surface. Measuring the time it takes for a beam to be reflected back will enable an accurate determination of distances. Conducting these measurements on the entire moon surface will allow the construction of a lunar topography model with never-before-achieved levels of precision and detail. Five different experiments will be conducted to assess the environment on and around the moon. lunar magnetometer, LMAG, charged particle spectrometer, CPS, plasma energy angle and composition experiment, PACE, radio science, RS, and upper atmosphere and plasma imager, UPI. Unlike the Earth, the Moon's magnetic field is extremely weak. Therefore, the sensor of the lunar magnetometer must be placed on the tip of a 12-meter-long mast so as not to be influenced by the magnetic field produced by the main orbiter itself, enabling precise investigation of magnetic field distribution. The charged particle spectrometer will measure alpha rays created from radon and polonium decay on the lunar surface and work to determine radon and polonium distribution and emission sources. The CPS also observes electron, proton, and baryon particles emanating from the Sun and other regions of the galaxy to determine the Moon's radiological environment. This data should eventually be of great use for future lunar exploration and development activities. Plasma around the Moon is generated by the Sun, the Earth's magnetosphere, and the lunar surface. The Plasma Energy Angle and Composition experiment has been designed to analyze and study the behavior of plasma energy around the Moon, as well as from the Moon and Earth's respective magnetospheres. The lunar missions conducted by the former Soviet Union are believed to have revealed the presence of a lunar ionosphere. This ionosphere has been said to either result from the breakup of electrons and ions from ultraviolet rays in the Moon's thin atmosphere, or from the electron layer on the lunar surface. When radio waves pass through it, distortions are produced. With the radio science, the Moon's ionosphere can be studied by measuring the existence of distortions in radio waves that reach Earth from the VRAD satellite. The upper atmosphere and plasma imager utilizes two telescopes highly sensitive to visible and extreme ultraviolet light to measure the terrestrial plasmasphere and the global distribution of the Earth's aurora and airglow from a lunar orbit. Two-axis gimbals on the main orbiter will enable directional control of the telescopes and automatic Earth tracking. Lunar gravity fields are to be studied using the two small satellites, the relay satellite, RSAT, and the radio source, VRAD satellite. Lunar gravitational pull varies from location to location, depending upon the different densities of subsurface materials. Therefore, radio tracking of the accelerating or decelerating main orbiter can reveal how the Moon's gravity is distributed. When the main orbiter is on the far side of the Moon, the relay satellite will relay radio waves from a ground-based station and the main orbiter, thereby conducting the world's first direct measurement of gravity fields on the far side of the Moon not visible from Earth. Radio signals sent from both the relay satellite and the VRAD satellite will be received at multiple locations on Earth. Through a method that simultaneously receives radio signals from stars and two small satellites, those satellite orbits can be accurately determined, and global observation of lunar gravity fields can be conducted at unprecedented levels of precision. The high-definition television HDTV system will be deployed on the mission, equipped with a telescope and a wide-angle camera. As the satellites move in the Moon's orbit, high-definition images of the Earthrise off of the Moon's horizon will be captured for education and public outreach. The 15 observation missions of Selene should provide the world with an immense corpus of valuable information and data for more accurately understanding the origin and evolution of the Moon. It should go a long way in helping us understand how the Moon was formed, what it's made of, what it is actually like across its surface, and interior structure.
Hello, me again. Before we go any further, I want to elaborate on one very important kind of instrument, as it'll come up throughout this video and in future lessons when we talk about Mars, the inner solar system, the outer solar system. You'll hear the word spectrometer a lot when I list off the kinds of instruments that different missions carried. I won't provide a full detailed breakdown here to the level of someone who actually does spectroscopy, because I don't. But I do know the basics, and they are critical for understanding how space exploration is conducted and why we know what things that we've never touched are made out of. Very basically, spectroscopy measures how light reflects off of objects. So to appreciate this, you need to be familiar with the electromagnetic spectrum, pictured here in a visual from NASA's Dawn mission. Dawn's not a moon mission, but I like the visual, so we'll use it. If you recall high school physics, you'll remember that light comes in different wavelengths. Critically, most human eyes only take in and interpret light in the visible range. You can see that there. But other kinds of light are also coming from the sun or light bulbs and bouncing off of things or reflecting off of them. When light from the sun or a light bulb reflects off of something, some of it is absorbed and some of it is reflected back out. Our eyes capture a portion of this, and our brains, like supercomputers, translate that into vision. Now, each element on the periodic table absorbs and reflects light in a mostly unique way, and that's very helpful because it has allowed physicists to essentially build up a sort of spectral catalog of the spectral signatures of different materials. So how does visible light reflect off of aluminum? How do X-rays reflect off of carbon? How does infrared reflect off of iron, etc.? These spectral signatures are really just plotted lines, and you can look them up easily online. So by now, you may be putting together how spectrometers help us know what the moons of Jupiter are made out of, or the surface of Mercury. Spectrometers on board spacecraft measure how sunlight, which comes in all wavelengths, reflects off of planetary bodies and enters the instrument's sensors. Mission scientists can then compare those spectral signatures to the known catalog of spectral signals here on Earth. So before we ever landed robots on the surface of Mars, this allowed us to look at Mars and say, hey, light is reflecting off of the Martian surface with the same spectral signature as light reflecting off of iron here on Earth. That probably means Mars must have a lot of iron in its chemical makeup. You'll notice there that I said probably. And that's because spectroscopy is not perfect. No science is. There's a lot of interpretation and a lot of messy data. There's a lot of interference. The filters need to separate different kinds of light. Materials aren't pure, so there's different kinds of elements in there mixed together, messing with the reflection. So there's a lot of interpretation and a lot of messy data, but it's far better than any other means of interpreting the composition of any materials. This imperfection in spectroscopy is why people like me say things like potential water ice or probably made out of and so forth, because some things haven't been observed enough or directly to say with more confidence. So anyway, that's a somewhat vulgarized description of spectroscopy, but I think it's all the basics you need to know moving forward for this class. You'll pick up probably a little bit more of it here and there as we go through the missions, and you can kind of now apply this to future missions talked about in these videos. But don't worry, we're not actually doing any spectroscopy in this class. Those of you in physics, chemistry, or geology may be doing so in your other courses, I suspect. But this is a broader interdisciplinary course, as you know, and that's really all you need to know about spectroscopy for now. So let's get back to Kaguya. So where does this so-called golden age of lunar exploration start? Well, it's a bit arbitrary, but I would say it was in the late 2000s and arguably started with the launch of the Kaguya mission, also known as the Selene mission. Kaiguya was a Japanese-designed and launched spacecraft. Its mission was to collect data that would help planetary scientists better understand the geological history of the moon and its evolution. To do this, it had a large suite of instruments, 15 in total, which is a lot for a single mission. Among these instruments were an X-ray spectrometer, a radar sounder, magnometer, a plasma imager, and a high-definition camera. Kaiguya also deployed two small satellites, Okina and Ouna. So it's two little satellites that were on board it, were put in orbit around the moon. Okina acted as a communications relay between the Earth and Kaiguya, while Ouna used interferometry to help map the moon's gravity field. We'll talk about that a little later with the Grail mission. Kaiguya entered into lunar orbit in October of 2007 and almost immediately began taking unprecedented high-resolution images of the lunar surface that you can see here. Within 6 months of its mission, the altimeters on board Kaiguya had collected enough information that global topographical maps could be created with Kaiguya data. The resulting global map was in places 10 times more detailed than previous lunar surface maps. Altimeters do this by pulsing laser beams down to the surface and measuring how long the return signal takes to reach the spacecraft. This, of course, is different depending on how high or low the feature it hits is. When the results are plotted over a long period of time, they can be used to create a topographical map or relief map. These topographical maps were combined with the high-definition images that you see to create the sort of 3D maps you're also seeing, where you can see relief in terms of craters and mountains and things like that. The Kaiguya mission ended in 2009 by impacting the moon as planned. Japan wasn't the only country sending spacecraft to the moon in 2007. That same year, China launched the Chang'e-1 lunar orbiter, the first mission in its new Chinese lunar exploration program. Now, unfortunately, there isn't a lot of imagery from the Chang'e-1 mission, so you'll just have to do it with my face for now, but trust me, as we get into future Chang'e missions, there's no shortage of interesting visuals. Chang'e-1 entered lunar orbit in November of 2007, carrying a laser altimeter, a stereo camera, a microwave radiometer, gamma and X-ray spectrometers, and a high-energy particle detector. We know from this mission and others that the moon is mostly made up of silica, the basic material that makes up most rocky material on Earth and in the solar system, and other major materials in the moon's composition include aluminum oxide, calcium oxide, iron oxide, magnesium, titanium dioxide, and sodium oxide. Again, for this course, we don't need to know all of this by heart, but you should know that the moon doesn't have, for example, abundances of hydrogen, nitrogen, helium, or other materials common on Earth or common on planets that have oceans and atmospheres. The Chang'e-1 mission's main objective were to collect information regarding future landing sites for the Chang'e program, which was already planning landers and rover missions as follow-ups. With its host of spectrometers, the mission also collected data on the location and distribution of elements that I just talked about, such as oxygen and iron on the moon. And lastly, in order to inform flight paths of future missions, the spacecraft collected data on the space environment around the Earth and the Moon, specifically solar winds and how they interacted with spacecraft and communications. Chang'e-1 operated from October 2007 to March 2009 in orbit around the Moon, and it provided China with vital information to advance future missions in the Chang'e program, especially regarding landing sites and solar winds and communication. Its laser altimeter also provided what was then now the highest resolution 3D map of the moon, surpassing that made of Kaiguya. So that's Chang'e-1. Let's move on. As we move into 2008, we come to the launch of Chandrayaan-1, the first lunar exploration mission from the Indian Space Research Organization, ISRO. The main component of the mission was an orbiter, somewhat similar to Chang'e-1, with objectives to image the lunar surface and collect data that would inform more complex future missions. Unlike Chang'e-1, Chandrayaan included international contributions, so while India built and operated many of the instruments that were on board, such as an X-ray spectrometer, a laser ranging instrument, and a terrain camera, the mission also included radar and imaging spectrometers from the US and the UK, while the European Space Agency provided a near-infrared spectrometer. Along with all these instruments on board, Chandrayaan also brought a small impactor probe with it. The probe was released by the craft after entering lunar orbit, where it then crashed into the south pole of the moon. The probe collected data as it descended and played a role in Chandrayaan's biggest discovery. That discovery was the positive identification of hydrogen-bearing signals, at the moon, hinting strongly at the presence of water ice on the surface. Two different instruments on board were able to identify a spectral signature consistent with hydrogen, indicating that water was most likely present, frozen, at various locations, most notably in permanently shadowed craters where the sun does not sublimate the material away. The extent of lunar water material remains debated, with current assumptions being that most of what might exist would be below the surface or mixed with lunar regolith in very small quantities. Overall, Chandrayaan was a tremendous success, but as 2008 turned to 2009, one of the all-time greatest missions to visit the moon would follow in the footsteps of Chang'e and Chandrayaan. As we look at some of its imagery, let's talk about the Lunar Reconnaissance Orbiter, or LRO. LRO was launched in 2009 by NASA and has been operating in orbit now for over 15 years. Its core objective was to map the moon in as much detail as possible. A large contribution to this has been the LROC instrument, or the Lunar Reconnaissance Orbiter camera, which has provided a global map of the moon at 50 centimeter resolution. LRO's radiometer has also provided a long-term data set on the moon's surface temperature and albedo, while the synthetic aperture radar on board supported and confirmed Chandrayaan's discovery of hydrogen-bearing minerals, or at least supported that finding, and the potential for water ice. Overall, LRO is one of the most important space exploration missions of all time. Its long-term observations and high-definition images have not only reshaped how the moon is understood by scientists, but has also informed the targets and objectives of subsequent missions from all around the world who have used LRO data to identify landing sites for landers and even traverse routes for rovers.
Cold, gray, lifeless, true, dynamic, complex, surprising, also true. Welcome to Earth's moon. For such a close neighbor, separated by a profound void, it mattered how we planned to visit. That's why NASA built LRO, the Lunar Reconnaissance Orbiter. Shortly after liftoff in June 2009, LRO began to transform our relationship. Because of LRO, we now know the moon's topography, its surface shape, better than any other planet in the solar system, including Earth. Why? Because most of the Earth is covered with this. But not the moon. There's more. LRO discovered the coldest measured places in the solar system, measured in craters that never see sunlight. Evidence that the moon has been shrinking relatively recently, and evidence of water ice at its surface. All by itself, LRO has amassed a trove of discoveries. But LRO has not been to the moon all by itself. Working in concert with several companion missions, LRO made careful measurements as other vehicles intentionally blasted through the dusty exterior to probe the structure of the moon's crust. What they learned is that we've barely scratched the surface of all there is to discover. The moon remains a cipher, a mystery, a puzzle box. Home to one of the oldest large craters in the solar system, the moon's surface is also a time machine, a witness to asteroid and comet impacts on Earth billions of years ago. The moon was pelted by ancient space rocks too. Through examination of those craters, we travel into the past. The more we learn about the moon, the more we learn about the early solar system, and thus our own planet, Earth. The moon becomes the rediscovered history book of our solar system's great library, returning a precious volume we thought might have been lost to the sands of time. For all its silvery promise in our night sky, it's not easy to visit our nearest neighbor, but the chasm of vacuum in between still hasn't kept us away. Every day, the Lunar Reconnaissance Orbiter continues to probe vital questions and amass essential data about a place close enough to light our nights and illuminate new dreams of adventure for future generations of explorers.
So that kind of wraps it up for the late 2000s, or the 2000s really as a whole. You may have noticed that there was quite a bit of diversity in the countries going to the moon, with each of China, Japan, India, and the United States sending major missions. Add to that the role of the European Space Agency in practically all of those missions, and you can see that lunar exploration for the purpose of science is a very international and collaborative endeavor. I'd say a big thing coming out of the 2000s missions would have been that identification of potential water by Chandrayaan-1 and LRO. The use of impactors was also relatively new and reflected the increasing complexity of space exploration missions in the 21st century. And as we'll see, especially in the Mars video, the complexity and creativity of getting things into space, into orbit, and onto the ground of other worlds continues to evolve. So while space exploration's made a lot of progress in the 2000s, all of it was from orbit. And as we move into the 2010s and the 2020s, we'll see that activity has increased on the lunar surface, with a focus on better understanding the surface environment in much more detail, often with the explicit intention being the potential return of astronauts from either the US or China or a host of other countries. In terms of major missions, I'd say the 2010s kick off with NASA's GRAIL mission, or Gravity Recovery and Interior Laboratory. The mission was designed to map the gravitational field of the moon, and it was launched in 2011. The mission was the first of its kind in planetary science, or at least space exploration, as it consisted of 2 spacecraft flying in formation around a planetary body. As the spacecraft orbited the moon, they were perturbed periodically by changes in the intensity of the gravitational influence of the moon. As there were 2 spacecraft, the differences in how the 2 spacecraft were affected were used to infer relatively minute changes in the moon's gravitational field and thus its internal structure. Using this method, GRAIL was able to map the upper layers of the lunar surface, the crust, and the lithosphere. It also provided information on the subsurface structure of the moon and the large impact basins where massive collisions hundreds of millions of years ago left large depressions in the lunar surface. The GRAIL mission also resulted in a detailed gravity map of the moon, allowing future missions to better understand challenges in approaching and landing on it. These maps and other data from the mission also allowed planetary scientists to discover subsurface openings formed by ancient lava flows, almost like underground moon caves. In 2012, the GRAIL mission ended with the 2 orbiters intentionally crashing into the moon. Of note, GRAIL was based on a similar mission from 2002 called GRACE, but GRACE was an Earth observation mission. Its gravity measurement techniques revolutionized environmental scientists' understanding of groundwater, one of humanity's most precious resources. From GRAIL, we move on to LADEE, another somewhat unique mission from NASA in that it had an odd focus for the moon, to explore the atmosphere. Now, the moon doesn't really have an atmosphere, but LADEE, or the Lunar Atmosphere and Dust Environment Explorer, intended to discover just how much of not an atmosphere there was around the moon. More specifically, it would aim to detect and measure trace gases and particles in the lunar environment. The mission was launched in 2013, and perhaps unsurprisingly, it found that the environment around the moon, what could be called the lunar exosphere, is very tenuous. In total, the gases and dust around the moon are 100 trillion times less dense than the Earth's, and for most purposes can be considered a vacuum. What little particles do exist in the moon's atmosphere are being recycled between the near surface and the surface through solar winds and impacts. Major events such as spacecraft landing on the surface also provide new materials to the tenuous lunar atmosphere, at least in very specific locations and for a very brief period of time. The LADEE mission took advantage of this, though, as the Chang'e 3 mission landed on the surface of the moon while LADEE was observing it. Both the lunar dust displaced by the landing and the propellant exhaust created by the rocket of Chang'e 3 were observed by LADEE, providing a unique data set on how materials dissipate back to the ground in the tenuous lunar exosphere. Along with confirming the presence and movement of materials in the lunar atmosphere, LADEE also identified the elemental composition of these materials, using its spectrometer to detect helium, neon, and argon, among other elements, in extremely trace amounts. No other orbital mission has focused on the lunar atmosphere since LADEE, but with an increasing robotic presence on the surface and the potential that humans could one day return to the moon as well, interest in how materials enter the quote-unquote air of the moon and settle back down could be of critical importance. While the surface is much less active than, say, Mars, the potential for moon dust to cover solar panels or communications equipment is worthy of understanding for future missions, especially if multiple spacecraft are landing and disturbing the surface near one another. While Grail and Laddie were unique in what they were measuring, the next mission was much less unique in its findings, but still a major milestone. In 2013, Chang'e 3 landed on the Moon. A small precursor mission, Chang'e 2, had followed up on the initial work of Chang'e 1, but it was Chang'e 3 that was really the next major step for the Chinese program. It included not only a lander, but also a rover, the first lunar rover since 1973, when the Soviet Lunokhod 2 landed on the Moon. Chang'e 3 made China the third country to land a spacecraft on the Moon and the second to operate a remote rover. Chang'e 3 was actually the first moon landing of any kind since 1976. The lander carried out analysis on the nearby lunar regolith and took a large number of images of its surroundings. It also used an ultraviolet telescope to observe distant astronomical features such as stars, galaxies, and quasars. The rover, named U2, or Jade Rabbit, carried a ground-penetrating radar as well as spectrometers to identify the composition of nearby materials. Like the lander, it took a number of images of its surroundings. U2 drove 114 meters, working mostly to characterize the physical environment of its landing site, image the Chang'e 3 lander, and conduct basic spectroscopy on nearby rocks and regolith. The rover ceased operations after about 6 weeks of its mission. Chang'e 3 was followed up by the historic Chang'e 4. Saw Chang'e 4 landed on Von Karman crater, making it humanity's first soft landing on the far side of the Moon. One of the challenges with operating a satellite on the side of the Moon that never faces Earth is one of communication. To solve this problem, China put a relay communication satellite into a halo orbit around the Earth-Moon L2 Lagrange point. The landing site, Von Karman crater, is within a massive regional crater called the South Pole Aitken Basin, which is thought to may still have exposed lunar mantle, or bedrock. Like Chang'e 3, the mission brought with it a rover named U-22. U-22 has now been operating for 5 years and carries with it a ground-penetrating radar, a spectrometer, a panoramic camera, and an instrument for detecting and analyzing how solar winds affect the lunar surface. Because no mission has ever touched down on the far side, practically everything Chang'e 4 and U-22 have returned has been novel information. Notable discoveries include rocks melted by previous meteorite impacts and new models of the lunar subsurface on the far side up to 300 meters deep. Jumping into the 2020s, India was also active advancing its lunar exploration. After the failure of Chandrayaan-2, the entire Chandrayaan-3 mission was a success, including an orbiter, lander, and India's first planetary rover. The mission landed on August 17, 2023, making India the fourth country to successfully land a mission on the surface of the Moon. The lander, Vikram, and the rover, Pragyan, touched down near the lunar South Pole, an area of particular interest for planetary scientists, not only due to the age of the surface, but also the presence of craters that often see no sunlight and the potential for ice to be present in those craters or below the surface. Over the first year of its mission, the Pragyan rover traveled about 100 meters. India plans to follow up the mission with Chandrayaan-4, a sample return mission. However, if Chandrayaan-4 is successful, it wouldn't be the first successful sample return mission from the Moon this century.
Next to China, state media there says the Chinese lunar probe has successfully taken off from the far side of the Moon to start its journey back to Earth. The Chang'e 6 module landed on Saturday in a volcanic basin close to the Moon's south pole and has collected samples of rock and soil. They're expected to be very different from rock formations on the near side of the Moon. The Chinese National Space Administration called the mission an unprecedented feat in lunar exploration. The probe is due to return in about 3 weeks' time to a landing site in Inner Mongolia. Well, let's hear now from our China correspondent, Laura Bicker.
They're calling this remarkable, historic. It's even trending on social media here. Their channel called Weibo, especially because the mechanical arm that was used to collect those rock and soil samples has put the symbol for Chongguo, which is China, into the Earth on the far side of the moon. They've also planted the Chinese flag on the far side of the moon. Now, the reason why scientists are so excited by this is because it's very, very difficult to control and even land and get an aircraft to take off from the far side of the moon, because there's no line of sight from Earth. So what China did was they launched a satellite which was there by April and ready for this mission, and they've used that satellite to relay messages. So for the last 2 days, the Chang'e 6 space probe has been collecting these precious rock and soil samples. Now, the other reason scientists are very interested in this is because in previous samples that you can see, the bit of the moon that you can see, they've collected the samples that look very volcanic, look very like you would see in Iceland or Hawaii. However, it is thought that the rocks on the far side of the moon could contain traces of ice. Now, that would mean there is some kind of source of water on that part of the moon. The reason.
Thanks to Laura for that. Right, we can speak now to astrophysicist Professor Quentin Parker from the University of Hong Kong. Thanks for coming on the programme.
Pleasure.
So what do you make, first of all, of just the challenge that has been successfully completed so far? We'll get on to the rocks and the ice in a moment, but just the logistics of doing what's been done so far. What do you make of it?
Well, it's never been done before in terms of a lunar sample return mission from the far side. Now, China has already landed on the far side. When it did that with Chang'e 4, that was the first time that's ever been done as well. And now it's the second time they've gone back to the far side, and this time they've done it to bring back lunar rock and soil samples. So that is very complicated. As was said by the previous speaker, there's no direct line of sight, so you have to have a relay satellite called Chukua, and that basically means magpie bridge. And the Chinese love having these interesting and lovely names for their missions. And that's kind of in what's called an L2 orbit around the moon that allows a direct line of sight from the lander to the satellite, from the satellite back to the Earth. So you can remain in communication at all times, which is vital for a mission of this type. So it's very complicated, very challenging technically. They've done it again. And now, just like the Chang'e 5, which is on the near side, they're now going to be bringing back, we hope, lunar rock from the far side rather than the near side.
Right, let's get on to this rock then. How much of it have they grabbed, and what's going to happen to it now?
They probably grabbed about the same amount as last time with Chang'e 5, because the Chang'e 5 mission and Chang'e 6 are basically the same in terms of the intent to go to the moon and bring back sample. About 2 kilograms is what they expect to bring back.
Okay, and what happens to it now when it's back on Earth?
Well, I mean, assuming they can get it back to Earth first, there's still a few hairy bits to go. They've gone back from lunar, from the surface of the moon into the spacecraft that'll then bring it back to the Earth. They're going to transfer the sample into the module, that re-entry vehicle that actually mustn't burn up in the atmosphere and come back safely to land in Mongolia. And once all of that happens, if it all does happen, because there's pretty scary parts there, then they'll just very carefully, like the Americans did with the asteroidal material that they recovered, carefully unpack and extract the material from within the lander.
And what will they be looking for?
Well, as was said previously, I mean, the far side of the moon looks very, very different to the near side. On the near side, you have all these mare, like Sea of Tranquility, which big lava fields from volcanic activity. That's pretty much absent from the far side of the moon for reasons that aren't completely understood. What you see on the far side is a much, very cratered terrain. Lots of bombardment happened, like on the near side, but it hasn't been washed over by volcanic lakes like it has on the near side. And so we think the geology is very different. And down in the South Pole, there are craters there which have high walls protected from sunlight at all times. And in those craters, we think there might be water ice and helium and other precious materials, which will be of great use to future exploration of the moon and even to habitation.
Interesting. And what does all this, as you've highlighted again the caveats, not over yet, not safely back yet. We appreciate those caveats. But if we presume that does all go swimmingly, what does this do you think, for the country's space endeavours?
Well, China's spacefaring events have been going gangbusters, I would say, for about 10 years. You know, they've had a very successful Chang'e series of lunar missions. They've also gone to Mars. They've also built a space station and about to put up a 2-meter class optical telescope like the Hubble, but with a field of view 350 times larger. So there's lots of things happening in the Chinese space program. This is just one of the most exciting. So the lunar missions haven't failed. They've all been successful so far, and everybody, any lunar scientist, any geologist worth his salt or her salt will be praying that this sample comes back in a pristine condition so it can be studied. And so, you know, it's going to be a veritable cornucopia of scientific delights, I think, that's going to come out from the geology of these different samples from the far side and the near side. And these samples are being shared. I mean, we got a sample at Hong Kong U. You know, and my deputy director, Joe Michalski, is American, worked a lot with NASA. He's going to be, he's working with that near side sample right now, and we hope to get a far side sample too. And around the world, I think Manchester University's got access to the Chang'e 5 near side moon rock. So, you know, it's not just China here. I mean, it's international collaboration, which is great.
Absolutely fascinating.
On June 25th, 2024, China became the first country to successfully return samples from the moon since 1976, and the first to successfully return materials from the far side of the moon. In total, nearly 2,000 grams of lunar samples were returned. The samples were scooped into a small capsule within a small descender spacecraft and launched back towards the Earth. Other than the sample return, the mission didn't really have additional science objectives. Chang'e 6 will be followed up by Chang'e 7 and 8, both of which will focus on finding water and other potentially useful materials for future missions by robotic spacecraft or humans. By 2030, China expects to land a crewed mission on the surface. So there we have it, the robotic exploration of the moon in the 21st century. Honestly, because the moon is somewhat basic, at least geologically, there haven't been a ton of super interesting discoveries in the past years as much as there have been really impressive feats of engineering. However, the detection of likely water in the South Pole is noteworthy, especially if someone can confirm and access that material and compare it to the water or hydrogen and oxygen on Earth. Remember that the current hypothesis for the formation of the moon is that it is the debris of a massive collision between two protoplanets, one of which was Earth. If the chemical composition of the water-like materials on the moon are the same as the Earth's, it will help planetary scientists advance that theory of the moon's formation and possibly even provide hints at where Earth's water came from. If the hydrogen materials on the moon are different than the Earth, then theories about the formation of the moon or how Earth got its water may need to be adjusted. Beyond that, the 21st century has seen a lot of mapping and physical characterization of the moon. Arguably, we understand the moon better than we do Earth. Part of that is in a large part because the moon isn't covered in water, and unlike the Earth, most of the moon, from our perspective, is unchanging. The physical characterization of the moon will be beneficial in the future should more advanced or even crewed missions take place. You'll see here I've tried to very simply, summarize the video, and when you look at it like this, you can see how each mission has either focused on a different aspect of the moon or completed a different feat. What all these missions combined to do then is slowly but surely advance our understanding of both the moon and Earth. A major milestone in this, of course, is the sample return by Chang'e 6, which has provided an entirely new data set compared to the Apollo missions, which of course all returned samples from the near side of the moon. Regarding those samples, planetary geologists will also aim to understand if the samples from Chang'e 6 provide any insight on the history of the far side and why it looks so much different than the near side with its lack of large dried up lava basins and plethora of craters. In the coming years, future missions, including those with astronauts, will collect even more material for analysis back on Earth and help provide answers to the questions I already mentioned, those questions about the moon's origin, its age, the near-side, far-side discrepancies, and the potential presence of anything that could be even remotely useful to longer-term, maybe weeks or months, long missions by humans. Until then, we have a lot of data to work with over 60 years of moon imagery and now materials available for students and scientists alike to work with. So, I hope you appreciate that over the last 25 years or so, we have advanced quite a bit in our understanding of the moon, but that a lot of science remains to be done.